Here you can see the converse part of Berge's theorem. So first you have to assume this. Assume G contains no M augmenting path. We are going to prove M is a maximum matching of G. To prove this, what you are doing is, first suppose M is not a maximum matching of G. You are taking like that because at the end you will bring the contradiction. Okay. So to do that, you are taking, suppose M is not a maximum matching. If M is not a maximum matching of G, then what will happen? There will be some other matching, and that matching will be the maximum matching of G, right? So that is what you are writing. You are taking that some other matching as M dash here. Let M dash be a maximum matching in G. If M dash is the maximum matching in G, then you can write like this, right? Number of, what is mean by this? Modulus of M dash. Modulus of M dash means number of vertices or edges. You can say edges also. That is, you can say number of vertices in M dash, or you can say number of edges in M dash. Both will give you the same result at the end. Okay, so that is okay. So let M, you are taking, let M dash be a maximum matching in G. So by the definition, number of vertices in M dash will be greater than number of vertices in the matching M. Am I right? That's obvious, right? Because M dash is the maximum matching. M is not the maximum matching here. So the number of vertices in M dash will be greater than number of vertices in M. In the next line, what you are doing is, you have to construct another one graph, that is H. Okay. How you are constructing, that is what we have wrote in this two lines. Set H is equal to graph of M symmetric M dash. Okay, so here you have to know what is, that is, you are drawing a graph of M symmetric M dash. What is M symmetric M dash? You are drawing a graph like this. For this, the M symmetric M dash is equal to this. You are drawing a graph for this, and that graph is called the H. Okay, that is what you are writing here. Set, can you see that? Set H is equal to graph of this, where M symmetric difference where this denotes the symmetric difference between M and M dash. I showed you the formula of M symmetric difference M dash, right? So using that, you have to construct a graph, and that graph is H. So in the next line, if you construct a graph like that, then that graph will look like this. This property will, that graph will possess this property. That is what you are writing in the next line. Each vertex of H, now you are having that graph H. Okay, in that graph you can have a vertex. Am I right? What you are saying is, if you construct a graph like this, what will happen is, there will be a vertex of H, and that vertex will have degree either 1 or 2. The degree of the vertex will be 1 or 2 in H. That is, the degree will be 1 or 2. In the next line, what you are writing is, the reason for saying this sentence you are writing here. Since it can be incident with at most one edge of M and one edge of M dash. Because the reason for having vertices of H degree either 1 or 2 is because the graph, you have constructed a graph with this. Right. So if you construct a graph like this, then what will happen is, it can be incident with at most one edges of M and one edges of M dash. To this vertex, there will be two edges, as you have said here. So one edge, okay, one edge is the edge from the matching M, and another edge will be the edge from the matching M dash. Okay, that is why you are saying the vertex of H has degree either 1 or 2. Okay, that is how you are writing these two sentences. Now, what you are writing is, now you are talking about the components of H. Okay, what is meant by component? H is divided into some other graphs. It is splitting. The H graph is splitting. Then only their components will be formed, right? So now in these lines you are talking about the components of H. So let's see what they are talking. Thus each component of H is either an even cycle, that is they are saying the component, two cases here you have, the component of H either will be either an even cycle or it is a path. Okay, I told you the H graph is splitted into components. So they are talking about the components will be either an even cycle or it will be a path. Okay, these are the properties of the components of this H. So in the first line what you are saying is, if it is an even cycle, how it will be. If it is a path, then how it will be. That is what you are writing in these two sentences. Thus each component of H is either an even cycle. If it is even cycle means with edges, the edges in that cycle will alternatively present in M and M dash. The edges, the cycle will have edges, right? So what they are talking is, one edge will be the edge from the matching M and another edge will be from the matching M dash. This edge from the matching M and another one from the matching M dash. Okay, that is what you are writing in this sentence. Or else if it is a path, if the component of H is a path, then what will happen is, path means it's a path. Okay, path. What they are saying is, if it is a path, then the edges will be alternatively in M and M dash. That is, one edge will be in M and another edge will be in M dash and another one in M. Okay, that like that. If it is a path, the edges will be present like this, or if it is a even cycle, then the edges will be present like this. That is what they are saying. H contains, if it is like that, then H contains more edges of M dash than of M. If it present like that, then what you will get is, H will contain more edges of M dash. From the, you have a matching M dash, right? The edge H, our graph H will have more edges from the matching M dash than M. That is what you are writing. Therefore, some path component P, you are taking path, the path you are denoting that path as P. Okay, you are taking that path from the graph H. That path, you are talking about a specific path here. Okay, you are taking a path P of H, and now you are talking about the path P here. That path P starts and ends with the edges of M dash. Okay, that path is starting and ending with the edges of M dash here. Okay, that is what you are writing. Okay, you are taking a path and that path is having origin and terminus. That origin and terminus edges are from the matching M dash. That is what you are saying. The origin and terminus of P being M dash saturated in H. It means the origin and terminus of the path P is M dash saturated. It means what? Origin and terminus vertices are present in the M dash matching in H, or that origin and terminus or M dash saturated in H, but that origin and terminus or M unsaturated in G. It means that origin and this, they are talking about an origin and terminus, right? So that origin and terminus is M dash saturated in H, but that same origin and terminus is M unsaturated in G. It means that origin and terminus is not present in the matching M in the graph G. That is what they are saying. So from this you can say here that origin and terminus is M unsaturated in G. Then by the definition of M augmenting path, you can say this path P is an M augmenting path in G. Hence the proof.